Hey guys, hi and welcome to chapter 4, which is all about atomic structure and periodicity. So we're going to be going over a lot of the things that I hope you learned in first year chemistry, and some of this, especially if you had me, should look pretty familiar. But if not, I'm going to guide you through it, and so we'll hit the highlights in chapter 7. And I suggest, like, to go along with this video, that you read sections 7.1 and 7.2 in your textbook, because it's always good to have that extra layer, of knowledge in there. So reading that and then going over this video with me will be helpful. Okay, so let's get started. I hope. Okay, here we go. All right, so we're going to be talking a lot today about light, and that is because the first, well, I should say, the later atomic models that we have that describe like what an atom is like in terms of like, where the electrons are and all that, those models were obtained by studying light. So like Bohr's model of the atom and our current model of the atom, the quantum mechanical model, heavily relied on looking at light. Yes, so Bohr's model, is the one that people often think of with the, nucleus and the electrons going around in the circles or orbits, as he called them. But that's not the most current model of the atom. Our current model is the quantum mechanical model that has been around for like about 100 years or so now. But Bohr in his model studied the line spectrum of hydrogen, and so the quantum mechanical model has a lot to do with light as well. Looking at if you had like a prism or a diffraction grating or something, and you could look out your window at the sunlight coming through the window, you would see that the diffraction grating or the prism, it would bend the light, and you would actually be able to see, instead of just white light that you normally see, you would see the light is actually composed of a spectrum of colors that looks kind of like the picture here in this drawing. So it's called visible light, the light that we, our human eyes can detect. So we can see, anywhere from red light all the way up to violet. And that corresponds to about 400 nanometers in wavelength to about 700 and something nanometers for violet. So you notice here that one color kind of fuzzes into the next color and then fuzzes into the next color. So that has a name, that kind of spectrum. And it's called a continuous spectrum because you see like all the possible colors in visible light. It looks like a rainbow, sort of. And so what you're really seeing is all the wavelengths and frequencies that our eyes can detect. So that's a continuous spectrum. And when you were maybe a youngster in school, did you learn the mnemonic device to help you remember the colors that are in a rainbow? Maybe. Does Roy G. Biv ring a bell? Yeah, so somebody a long time ago made up this little thing to help you remember the colors, but it's, it stands for red, orange, yellow, green, blue, indigo, and violet. So those are the colors, with the red being on the longer wavelength and the violet being shorter wavelength. But is that the only kind of light that there is? Well, no, right? There's lots of different kinds of energy out there that we're getting from the sun and, generated by other things. And we call that all of the forms of radiant energy. We call that the electromagnetic spectrum. And here's a little video about that. It's from the NASA people. And I showed it to you if you had me for first year chem, but I'm not going to do that right now. But look it up. It's a nice little 5-minute video from NASA. But the electromagnetic spectrum, the deal with that is that all forms of electromagnetic radiation travel at the same speed. We call that the speed of light, which is pretty darn fast. It's 3.00 times 10 to the 8th meters per second. Pretty fast. So that is a constant. So can you think of any other forms of electromagnetic radiation besides visible light that we've been talking about with all the colors? There are other forms that you can't see. Our eyes are just not made to do that. But can you think of any? What if you break a bone and you have to go to the doctor to get checked out? Yeah, they're probably going to do an X-ray on you. So X-rays are a form of electromagnetic radiation. Let's see what others we got here. Well, the real high energy ones, the damaging ones, are called gamma rays, and you don't want to be hit by those. That would be put off by a nuclear bomb and everything. It's not good. All right, like I mentioned, X-rays, also pretty high energy. That's why they protect you, like when you go to the dentist or something and you're getting your teeth x-rayed, they protect the rest of your body by putting a big kind of heavy lead apron on you to absorb some of those x-rays. Ultraviolet light, that's the stuff that comes, from the sun, and we wear the sunscreen to try to protect our skin from the ultraviolet light. Ultraviolet also being used, as like a disinfecting kind of light too. Just for your information, I saw them disinfecting some masks the other day that doctors were wearing in this COVID-19 era here. Okay, then we also have visible light. We've got infrared, and they make goggles so you can see kind of at night. You can detect the heat given off by, things that are living, or I guess like things that have absorbed heat. And then we have like radar and microwaves, TV and FM radio waves, and shortwave radio, and AM radio waves. Okay. So if you look over here, like you can see how they kind of rank, and we're going to talk about wavelength and frequency in a minute here, but these have a longer wavelength on this end of the spectrum, and a shorter wavelength over here where the ultraviolet X-rays and gamma rays are. All right. So one thing that you want to know about is to be able to work with a couple of characteristics of waves. The first one being the wavelength, which is the distance between consecutive wave peaks. So if you had a wave going by and you measured the distance between the peaks, that's called a wavelength. And it has in its name length, right? So that would imply that it is a distance measurement. So the units that would go with that would be distance units, like meters, centimeters, nanometers, because nanometers is on the order of the size of an atom. And 1 times 10 to the 9th nanometers equals 1 meter. That's kind of a good one to know. There's also this special unit called an angstrom. It looks like a capital A with a little halo on it. And that's 1 angstrom, or sorry, 1 meter is 1 times 10 to the 10th angstroms. And you notice here, wavelength, I didn't make this up, but somebody did. They gave it the symbol, the Greek symbol called lambda. And it looks like somebody who's kind of, I don't know, leaning backwards or something, but it's a Greek symbol. All right, the other characteristic of waves you would want to know about is frequency, which is if you were standing here, say you're up here, and here you go, and you count the number of waves that go by in a second, that's called the frequency of that wave. And it also has a Greek symbol. It looks like a V sort of, and it's the Greek letter nu. And it has special units. You're counting sort of like wave cycles that are passing by per second, but they don't normally write the wave cycles part, right? So that's kind of gone. And usually they'll either write it as 1/seconds, which is the same thing as seconds to the -1, or you see this very often, hertz. That's the SI unit for frequency. So the symbol is Hz, and 1 hertz is equal to 1/seconds or inverse seconds. Okay? All right, so we got lambda, that's wavelength, and we've got nu, that's frequency. All right, so here's a little quiz for you. Here's 3 waves, A, B, C. Which of these waves do you think has the longest wavelength? Like, that would mean they have the biggest distance between wave peaks. What do you think? Did you say wave A? Yeah, because it has a pretty good amount of space between the wave peaks. And of these 3 waves, it has the longest one. All right, which do you think has the highest frequency? Now remember, frequency is the number of wave peaks going by in a second. Did you say wave C? Yay, good for you. How about, and we haven't talked about this yet, but you can relate the frequency of a wave to its energy. So just what does your gut tell you about these waves? Which one would have the greatest amount of energy? Did you say wave C? Yay, good for you. So it has a high frequency, which means that it has a high energy as well. Okay, more quiz here. So here's the whole electromagnetic spectrum. And over here is kind of like, shows you the wavelength and also down here the frequency. So which form of electromagnetic radiation do you think has the shortest wavelength, the shortest distance between wave peaks? Did you say gamma? Yes. Gamma rays have the shortest distance between wave peaks, so they have the shortest wavelength. How about the longest wavelength? All right. Did you say radio waves? Good. Well, radio waves can be on the order of meters long, so they're pretty, have a long wavelength. How about the highest frequency? What would have the highest frequency? I think that would be gamma rays again. How about the lowest frequency? That would be radio again. All right, which of these would have the greatest energy? Did you say gamma? Yeah. How about the least? Radio. All right, so that's an introduction to the electromagnetic spectrum and wavelength and frequency. What we want to look at next is what is the relationship between wavelength, lambda, and frequency, nu? Do you think that they are inversely related or directly proportional? What do you think? Well, if you said they're inversely proportional, as in like if the wavelength goes up, like radio waves, you have a long wavelength, the frequency goes down, you have fewer waves going by in a second. You're right. And so the equation to relate them is this one here. C equals lambda times nu. C is the speed of light that we talked about earlier. And if you had me before, I told you that when I took chemistry in 11th grade in high school, my teacher, who was Mr. Robertson, and Ron Robertson was his name, R squared is what we called him. He made us like stand up and do this like as a cheer to help us remember the equation. So he called it the Go Lambda Nu equation. Like it was sort of a fraternity or sorority cheer. You know how they have those Greek names for sororities and fraternities. All right, let's look at this. So Go Lambda Nu. The go part is c, the speed of light. So remember, that's a constant, and it's everything, all kinds of electromagnetic radiation travel at that same speed, which is 3.00 times 10 to the 8th meters per second. So that was the go part in the equation. And then we have lambda, which is the wavelength of whatever electromagnetic radiation you're talking about. This has to be in meters. So notice that. And that the reason is because we're defining the speed of light in terms of meters per second. So we've got to have the wavelength in meters. If it's not, we'll have to convert it to meters. And then finally, we have the new part of the equation, the frequency. And so remember that is 1 over seconds, which is the same as seconds to minus 1, which is the same as hertz, Hz. Okay, so let's see if we can do some problems with Go Lambda Nu. All right, here's our first one. We have some yellow light, and it's being emitted by the sodium lamp. And we know the frequency of the radiation is 5.10 times 10 to the 14th inverse seconds. Okay, so this is the frequency. And you have to get used to these Greek letters, but don't let it bother you. This Go Lambda Nu equation is given to you by the AP people. And what the symbols mean, I believe, is also defined. All right, so that's the frequency. We're asked to calculate the wavelength of this yellow light. So we're looking for lambda, which is the wavelength. And we always know the speed of light, c. All right, so this is a plug and chug kind of thing, right? We know the equation, C equals lambda nu. Plug in the speed of light for C. And wavelengths, we're going to solve for that. So just think of that as x, you know. And we're going to plug in the frequency, 1/seconds. All right, so we got to algebraically just solve for lambda. So that means we're going to have to divide both sides by 5.0 times 10 to the 14. So let me do that here. Okay, so I get 5.88 times 10 to the minus 7 meters. So this is my wavelength of light. And typically, like here we're talking about visible light. It's a color we can see, yellow. A lot of times visible light will be something times 10 to the minus 7 meters in length. All right, let's keep going. All right, we've got here some mercury atoms that are emitting light with a wavelength of 436 nanometers. What is the frequency of this radiation? And what color of light do you think is associated with this wavelength? Now, that's a question, that second part, that they could ask you, but they would give you probably a chart with the colors and the corresponding wavelengths, so you would have some reference to, you know, look at. I don't think they expect you to memorize like colors of visible light. So, right, lambda, the wavelength is 436 nanometers. We're looking for the frequency, and of course we know the speed of light. Now remember what I said about, like, if you don't have meters, like we don't here, we have nanometers, we need to convert that over to meters first before we plug it into the Go lambda nu equation. All right, so we need to convert nanometers to meters. And this is a conversion factor. 1 meter over 1 times 10 to the 9th nanometers. So we plug that into our calculator, divide it out, and you should get 4.36 times 10 to the minus 7 meters. Now we're ready to plug this into our Go lambda nu equation. Okay, C, 3 times 10 to the 8th meters per second equals to lambda, 4.36 times 10 to the minus 7 meters, times nu, the frequency. So we're going to solve for the frequency and just got to plug that in the old calculator. All right, I get 6.88 times 10 to the 14. And you got to think about what's the unit for frequency? Well, it should come out to be 1/seconds or hertz. Okay. Okay, then, what color of light do you think this goes with? Well, we'll have to go back and look at some examples. Let's see if I can get back there. Let's see. So we had, let's see, 6.88 times 10 to the 14th hertz was our frequency that we found out. So looking around in here, here's 10 to the 12th, 10 to the 15th. So it's probably, oh gosh, maybe somewhere in there, would you think? You know, So maybe it's in like sort of that purple or violet range, most likely, possibly the indigo. Okay, going back here. So we'll say blue or violet, something like that. Okay, so they would have to give you a chart for you to look at. All right. So we keep going here. So we saw that, like, if you look at light, regular ordinary sunlight through a prism or a diffraction grating, it breaks that light up into a continuous spectrum, like a rainbow, where you see every color. But not everything makes that rainbow kind of spectrum. For instance, if you take an element and you heat it up or you zap it with some electricity, that element also gives off light, but it doesn't give off every color in like rainbow. It only gives off certain colors of light, which show up in a spectrum that's called a line spectrum or an atomic emission spectrum. So these elements, which of course, an atom has electrons in it, those electrons absorb that heat or electrical energy that you're supplying to the atoms. The electrons actually move up in energy level. And then when they fall back down to their normal state, called a ground state, they emit that energy in the form of light that you can see. And that's what we call the line spectrum. Yes, so if you're looking at it with like a diffraction grating, you would see, instead of a rainbow, you'd see distinct colors of light, that corresponded to a specific wavelength and frequency. And we would, if we were in class, I could show you some of that with the gas spectrum tubes, but don't have that with me here at home. So, one of the scientists who was trying to study light given off by, like, an object when it's like so hot, like you've heated it so hot that it's like glowing. This guy's name was Max Planck. So this was like around 1900. He tried to come up with an explanation for how this light was given off, and it's sort of a complicated thing. But basically, all of the old theories didn't work for him. So he kind of threw everything in the trash, and he came up with this new idea called quantum theory to try to explain how these hot glowing solids, or actually black bodies, they called them, were giving off light. And in 1905, a guy you probably are familiar with, Albert Einstein, also built off of Max Planck's work and extended that quantum theory to explain all forms of electromagnetic radiation, not just light that you can see, visible light, but he applied quantum theory to every kind of electromagnetic radiation. So what is quantum theory that was proposed by Planck? But basically it says that the light that is emitted by these electrons in atoms, as they go from a higher energy state, which is called the excited state, to a lower energy state, the ground state, that light is given off not in a continuous stream or wave like we normally think of light. Light has a lot of properties of waves, such as being able to be bent or refracted or reflected, like by mirrors and so forth. But it also has properties not only of waves but of particles. And so Planck was trying to describe light given off as though it were in discrete amounts, or these little particles or packets of energy called quanta. Einstein called them photons instead of like a continuous wave. So you can kind of think of quanta or photons as particles of light. And so what we now have is this idea called the wave particle duality of light, that light actually has properties of both waves and particles. Kind of weird. So Einstein, what he said was that you could view electromagnetic radiation, any kind, as sort of a stream of particles. And so he's the one that used the term photons. And what he did was he studied this phenomenon called the photoelectric effect. And what it was like taking, let's see, you had a piece of metal here, and you have some light source up here shining down on the metal surface. What he found was that in some cases, if you had a certain threshold frequency of light, like you had light with at least this frequency, then electrons here on the surface of the metal could be bumped off or ejected off the surface of the metal. But it didn't happen for any old frequency. It had to be like a certain frequency for that metal or higher for the electrons to be bumped out. And even like they tested out, like even if you put like high intensity light, just like, just like bombarded the metal surface with this high intensity light, it didn't matter about the intensity. You had to have that certain frequency to make the electron to jump off the metal surface. All right, so that led Einstein to look at the energy of the light and the frequency of the light and how they were related. And what was found was that as the frequency was higher, the energy of that photon or quanta was also higher. And we call that Planck's equation now. And here's another equation that's given to you by the good old AP people. The equation is E equals H times nu, and nu is still the frequency that we've been talking about, right? So the big E in the equation stands for the energy of one quantum or photon of light that is emitted by electrons moving around, right? So electrons move up in energy when they absorb heat or electricity or something, and then they move back down and they emit energy. So if you're talking about emitting one photon of energy, then this is the equation for that. And you know from our study of thermochemistry that energy has the unit of joule, the capital J. The H in this equation up here is also a constant, kind of like the speed of light. So it was named after Max Planck. So it's called Planck's constant. It is this value always, right? It's a constant. And this is another number along with the speed of light that the AP people would give you. So it's 6.63 times 10 to the minus 34 joules times seconds. So it has a combo unit to it, right? Joules times seconds. And nu, that V looking thing, is still the frequency of the energy given off by this particular electron, right? So it's still 1/seconds or hertz. All right, let's see how we can use Planck's equation here. All right, so we're looking at a quantum of light, and then we know the frequency of it. 8.12 times 10 to the 14th hertz, or 1 over seconds. And we want to know what is the energy of this quantum that's being given off by an electron moving around. Sorry, question mark. So we're looking for energy. We know Planck's constant. So if we know two of those things, we can solve for the energy. So we can use this equation developed by Einstein, Planck's equation. E equals to h nu. So we just have to plug in what h is, Planck's constant, and plug in the frequency. Oh, shoot. Sorry. Must be at the edge here. I'll write it down here. Okay, scribble that out. Okay, so we just got to multiply those two numbers together. Look how the units are going to work out. We have joules seconds times 1 over seconds. So that the seconds over seconds is going to cancel. And we'll end up with joules for our unit, which is good because we're solving for energy. All right, let me punch that in. 6.63 times 10 to the minus 34. And then times 8.12 times 10 to the 14. Okay, I get 5.38 times 10 to the minus 19 joules, which is a small number, but remember, we're only talking about like a very tiny amount of energy given off by one electron. If you had more than one electron, you could multiply it by a factor of n there, but we're talking about one electron here. Okay, let's try another one here. And then that'll be kind of the end for today. All right, Planck's constant. Sorry, didn't mean to say that. All right, this is another example of using Planck's equation. That's what I meant. All right, again, we're looking for what is the energy of light with a wavelength 662 nanometers. And you say, wait a minute, Planck's constant? Planck's equation, that's E equals h times nu, the frequency. I don't have frequency in this particular example. What am I going to do? Oh, that's right. I know this equation. Yeah, I know Golan's and nu, and I know Planck's equation. So if I'm given the wavelength here, which incidentally I would want to convert over to meters, which would be 6.62 times 10 to the minus 7 meters. If I know that, then I can first use equals lambda nu to get the frequency, and then I can use this guy, Planck's equation, to solve for energy. Aha, okay. All right, so I'm going to solve for frequency, and I'm going to plug in the speed of light for C, and that equals to the wavelength, 6.62 times 10 to the minus 7 meters times frequency. All right, I solved for frequency. Hold on. Okay, did you get 4.53 times 10 to the 14? 1 over second. Hope so. All right. Now we know that we can plug it into the Planck's equation because we know H, 6.63 times 10 to the minus 34 joule seconds times the frequency we just figured out, 4.53 times 10 to the 14, 1 over seconds. Our seconds will cancel out with each other and we'll have joules for our final unit there, 6.63 times 10 to the minus 34 times 4.53 times 10 to the 14. I get 3.00 times 10 to the minus 19 joules for my answer. All right, so that little electron would be giving off 3 times 10 to the minus 19 joules of energy. All right, so that's it for today. And again, I suggest read sections 7.1 and 7.2 because that goes over all this stuff and hopefully could answer any questions that you have. All right, I'm going to give you some practice problems to do using the Go Lambda Nu equation and Planck's equation. And those you would want to submit in the Dropbox in Veracross. All right, thanks guys, and I'll see you back here tomorrow. We'll get into the quantum mechanical model and electron configurations. Woohoo! Bye!